Hi everyone, this is Dr. Nak. Today we're going to be learning about zeros of polynomial functions. We're going to be learning a lot of objectives in this section, so as goals, let me just write down everything that we're going to learn. The first thing is this: we're going to learn how to evaluate a polynomial using this thing called the Remainder Theorem. Number two, using the Factor Theorem to solve a polynomial equations. Number three, use the rational zero theorem to find the zeros. Number four, find the zeros of a polynomial function. Number five, use the linear factorization theorem to find the polynomials with given zeros. Number six, use Descartes' rule of signs. Dear Lord, do you see how many theorems that we're going to have to go through? We got the Remainder Theorem, Factor Theorem, Rational Zero Theorem, Linear Factorization Theorem, and Descartes' rule of signs. We're going to get through this together. So let's take one thing at a time. So let's start from goal number one, which is the Remainder Theorem. So here it is. This is the Remainder Theorem. It says let f of x be a polynomial if f of x is divided by x minus c, then the remainder is f of c. Before we go over an example, let's review the division algorithm for polynomials. Now, if I wanted to divide 53 divided by 4, that's equivalent of writing in a long division form 53 divided by 4. Then you ask yourself how many times is 4 is going to go into 5, so that will be once. And you subtract, so you're going to have 13. And then how many times is 4 going to go into 13? That will be 3 times. So you said this is 3 times 4 is 12. So it looks like our remainder is going to be 1. So remember all those terminology. Now this is called a dividend. And then this guy is the divisor. And this number is called a quotient. And then, of course, the last guy right here is the remainder. All right, so how do you express 53 divided by 4? That's same thing as 53 divided by 4. So that's same thing as 13, right? And then plus the remainder over the divisor. So in general, let's pretend our f of x is the dividend. I color-coded. And then the divisor is our g of x. Then I can write our long division of the form f of x over g of x equals the quotient plus the remainder over the divisor. Now what I'm going to do is this. I'm going to multiply everything by the least common denominator, which in this case our g of x, which is the divisor. So let me just do that. So if I multiply this side by g of x, whatever I do to the left, I better do the same thing to the right. Now I'm going to distribute. Now if I multiply this out, then our g of x is going to cancel out on the left hand side of the equation. And then what you're left with is, let me just write everything out. Now remember, I am distributing this g of x to each term. So our next term is going to be q of x times by g of x. All right, and then plus, now if I distribute g of x to r of x over g of x, then these g of x is going to cancel out. So what you're left with is just the r of x. So notice that what we can do is this. We can write dividend equals quotient times the divisor plus the remainder. So basically what the theorem is telling you is this. If f of x is divided by x minus c, so here's my f of x, and our g of x in this case is going to become x minus c, then we can compute the remainder of that function. That's pretty cool, isn't it? But anyways, what is that remainder? Well, if it's the divisor's x minus c, then all you have to do is take your function f and then evaluate that at c. And that's going to be the remainder value. So let's do an example. Example 1, find the remainder when f of x equals x cubed minus 4x squared minus 5 is divided by x minus 3. Now first, we need to determine the value of c is going to be. So remember the theorem. Theorem says that if the divisor looks like x minus c, then the remainder is going to be f evaluated at c. So that c value is very important. And in order to find c, there better be a minus sign between the x and that number. So in this case, everyone matches up nicely. So our c in this case is going to be 3. So let me just write that out. So in this case, our c equals to 3. Yes, of course, you can use the long division of polynomial to find the remainder, but remainder theorem should be much easier if we just want to find the remainder of the polynomial divided by x minus 3. So let's do it then. Okay, so applying the remainder theorem, so by the remainder theorem, THM means theorem, the remainder is going to be f evaluated at c. So in this case, it's going to be f of 3. So this is going to be 3 cubed minus 4 times 3 squared, and then minus 5. So this is going to give us 27 minus 9 times 4, that's 36, and then minus 5, so which is going to give us minus 14. So it looks like our remainder is going to be negative 14. You know what? Let's check by doing the long division. Okay, so let's do this. So we have x cubed, so let's write down our dividend. So you're going to have x cubed minus 4x squared, and we're missing the x, so we're going to put 0x and then minus 5, and whole thing divided by x minus 3. Oh, I guess we can use the synthetic division, huh? But anyway, so I just wrote it this way, so let's just do it. So what times x is going to give us x cubed? That will be x squared. So you're going to go x squared times x is x cubed, and then minus, you're going to have 3x squared. Draw the line, change the sign on the bottom, and then add vertically. Then we're going to have negative x squared, and then I'm going to drop down the plus 0x. So then you're going to have to ask yourself, what times x is going to give us negative x squared? So that will be just negative x. So here you're going to have negative x squared. Oh, what did I put? Cubed. Negative x squared, and then you're going to have plus 3x. Okay, draw the line, change the sign. So you're going to have plus, minus. So then here you're going to have minus 3x. We got to keep going. Drop down that negative 5. So now what do we need to do? So you got what times x is going to give us negative 3x. So that will be negative 3. So you're going to have negative 3x and then plus 9. All right, so what do? Draw the line, change the sign on the bottom, and then you add vertically. And look, your remainder is going to be 14. I mean negative 14. So it matches. So if you're just asked to compute for the remainder, right? Which method was easier? The long division or by using the remainder theorem? I say remainder theorem 100%. Our next agenda is going over the factor theorem. Now, the factor theorem falls directly from the remainder theorem. So let's just see what it says. Factor theorem says that let f of x be a polynomial function. Then x minus c is a factor of f of x if and only if f of c equals to 0. Which should kind of make sense if you think about it, because if x minus c is a factor of f of x, right, then do you see that the remainder has to be 0? Now, from the remainder theorem, if f of x was a polynomial, then f of c was the remainder, isn't it? But look at it. This is telling you that if x minus c is a factor of f, then the remainder, f of c, must be 0. So this statement does make sense. Now, let me try to explain this if and only if statement. So in this whole entire factor theorem actually consists of two separate statements. So the first one would be if f of c equals to 0, then x minus c is a factor of f of x. And the second one would be if x minus c is a factor of f of x, then f of c must be 0. So every time you see this word if and only if in a math theorem, which means that for sure you're going to have two separate statements. But anyways, let's do some examples. Example number 2, determine whether the function f of x equals 2x cubed minus x squared plus 2x minus 3 has a factor x minus 1. So basically what the question's asking you to do is this. Okay, if x minus 1 is a factor, right, then you should be able to write your f of x in terms of x minus 1 and then multiplying here by some other polynomial. Now when you multiply it out, you better get the given function. But anyway, so let's apply the factor theorem. So it says that if x minus 1 is a factor of f of x, then f of 1 must be 0. So that means that in order to determine whether x minus 1 is going to be a factor of f of x, we just check f of 1. All right, and then cross our fingers that that's going to equal to 0. All right, so let's check. All right, so f of 1. Okay, ready? So we're going to have 2 times 1 cubed minus 1 squared plus 2 times 1 and then minus 3. So that's 2 minus 1 plus 2 minus 3. So, yay, that's going to go to 0. So look at it. We have f of 1 equals to 0. So that means that if I divide our f of x by x minus 1, the remainder is going to be 0. All right, so therefore, yes, x minus 1 is a factor of f of x. Let's do another one. Let's check to see if x plus 2 is going to be a factor of the same f of x. All right, so what do we need to do? We need to check is f of 2, be careful here. I almost said f of 2, sorry. So this is x minus 2, right? So what we need to do is we need to check if f of negative 2 is going to be 0 or not. All right, so let's go. So here we're going to have 2 times negative 2 cubed minus negative 2 squared plus 2 times negative 2 and then minus 3. So this is going to be negative 16. And then negative 2 whole quantity squared is going to give us positive 4. So you're going to have a minus 4 and then another minus 4 and then minus 3. And that gives us negative 27. Which does not equal to 0. All right, so that tells us that x plus 2 is not a factor of f of x. So if you divide f of x by x plus 2, for sure you're going to get some kind of a remainder. Do you all want to check to make sure this statement is legit? You know what? Why not? Let's just check. So let's check, is x plus 2 is a factor of our f of x? Well, we already know what the answer is. Answer is no. Okay, so let's do a long division, or we can do synthetic division in this case, just to see if there is going to be any remainder or not. All right, so let's go. So here our c is going to be negative 2, right? And then let me just write down the coefficient. So you got a 2, negative 1, and then 2 and a negative 3. So I'm going to draw the line, drop down the first number, and then you multiply 2 times negative 2, so you get a negative 4, add negative 5. Multiply negative 2 times negative 5, which you're going to get 10. Add, you get 12. Multiply negative 2 times negative 2 times 12, so that's going to give us negative 24. So look at it. We're going to have a remainder of negative 27, as we expected. Okay, so this just tells us that our f of x is going to be x plus 2 and 2x squared minus 5x and then plus 12, right? You so want to stop right there because that looks clean, but not in this case, okay? Because we have a remainder. So here you're going to have minus the 27. So it makes sense. Now moving on to our goal number 3, to learn about the rational zero theorem. So let's see what it says. Rational zero theorem. Let f of x be a polynomial function of degree 1 or higher of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus yada 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 plus a sub 1x plus a sub 0, where a sub n does not equal to 0 and then a sub 0 does not equal to 0, where each coefficient is an integer. Coefficient means each a sub n minus 1, and so forth. Now, here's the statement. If P over Q in lowest term is a rational zero of f, then P must be a factor of a sub 0, and Q must be a factor of a sub n. I know, the statement and the notation looks really scary, but there's nothing to it. So, first of all, right, they're basically saying is that if there is a rational zero, now rational means fraction, okay, so if there is a fractional zero of f, then P must be a factor of a sub 0. So P must divide a sub 0, whatever this constant is. And then Q must be a factor of a sub n. So that means that Q must divide the a sub n. A sub n is your leading coefficient. Now again, rational zero means that it's just a fractional zero, which is denoted by P over Q. So basically, this is going to be our game. Given a polynomial function, right, we want to find the zero of f of x. Okay, but how are we going to find it? Well, we're going to have to get all the factors of a sub 0 and then all the factors of a sub n. And then we're going to combine that to make all the possible P over Q's. Now, those are all the possible fractional zeros. Now, if P over Q is a 0 of f of x, right, then do you see that by the remainder theorem, if I plugged it in that P over Q in here, your resulting value should be 0. But anyways, let's do some examples. Example 3. Find the real zeros of the polynomial function f of x equals 2x cubed plus 11x squared minus 7x minus 6. Now, real zeros means that our zeros better be a real number, not a complex number. Alright, so first step is this. We need to list all the values for P and Q. Okay, so again, let's note that P must be a factor of a sub 0. So P must be a factor of our a sub 0, which is a constant term. So in this case, it's negative 6. And then Q must be a factor of our leading coefficient. So our leading coefficient is 2. Let's start out with all the possible values for P. Okay, so P must divide negative 6 nicely. So I can think of positive or negative 1 will go in there nicely. And then what about plus or minus 2? And then plus or minus 3, and then plus or minus 6. Now let's go with our leading coefficient, a sub n. So in this case, that's 2. Also, this one's much smaller value. So you got q equals to plus or minus 1, because I can divide 2 by either positive 1 or negative 1. And then you're going to have a plus or minus 2. Now, step 2, what we need to do is form all possible P over Q's. All right, so ready? So all the possible values for P over Q. All right. Oh, this one's not too bad because our denominator only has 4 terms, plus or minus 1 or plus or minus 2. But anyways, first what we're going to get is plus or minus 1 over plus or minus 1, and then plus or minus 1 over plus or minus 2. So let me just write that out. So you're going to have plus or minus 1 over 1. So it's still going to be 1. All right. And then you're going to have plus or minus 2 over plus or minus 1. So you're going to have plus or minus 2. So if you want to take plus or minus 1 on the denominator, basically I have to list everything out, because you're going to have 1 over 1, 2 over 1, 3 over 1, 6 over 1, and so forth. So let me just write that out. So you're going to have plus or minus 3 and then plus or minus 6. Now let's take care of the denominator being plus or minus 2. So here what we're going to get is plus or minus 1/2. That's the combination of plus or minus 1 over 2. Now the next one, I'm going to go plus or minus 2 over plus or minus 2. So 2 over 2, that's 1, isn't it? So we're going to get plus or minus 1, but we already listed there, so we don't need to do that. All right, so the next one will be plus or minus 3 over plus or minus 2. So we don't have that yet, so let's just write that out. All right, and then the last one, plus or minus 6 over plus or minus 2. But that's just going to be 6 over 2, that's 3. So we're going to have plus or minus 3, but we already have that. So this is all our possible zeros of our function f of x. Now guess what we need to do? Yes, you need to get your trusty calculator out, because what we're going to do is we're going to plug it in each of these values. All right, including plus and minus, and then we're going to plug that value into f of x. All right, now if the outcome of f of p over q equals to 0, then what we can conclude is that that number p over q must be a 0 of our function f of x. Anyways, let's do it. Step number 3. Now we're going to find all the zeros of f of x. So that's same thing as compute f of p over q. Now what we're hoping to get is, if I plugged it in p over q into f, we're going to have 0 as a result. So here are our possible zeros, so we must check. So what do you want to do first? So maybe I should write down our f of x as well, right? So let me just write down our f of x. So here's our f of x, 2x cubed plus 11x squared minus 7x minus 6. All right, so let's do this. Now, if I plugged it in plus or minus 1, right, I don't think it's going to add up to a 0. So I'm just going to skip that, and then maybe we can check plus or minus 2, plus or minus 3, plus or minus 6. Let's do the fractions at the end. All right, so let me go check. Oh, goodness gracious. Get your calculator out, people. So we're going to do f of 2. So we got 2 times 2 cubed plus 11 times 2 squared minus 7 times 2 minus 6. My trusty calculator said that's going to equal to 40, which does not equal to 0. Wah, wah, wah. All right, now let's check f of negative 2. I don't think this is going to go to 0 either, but what the heck. So you got a 2 times negative 2 cubed plus 11 times negative 2 squared minus 7 times negative 2 and then minus 6. I knew it. My calculator said this is 36. Nope, that does not equal to 0. All right, so here we go. F of 3. You got 2 times 3 cubed plus 11 times 3 squared minus 7 times 3 minus 6. No, this is 126. Yikes, nope, that does not equal to 0. Okay, we do not give up. All right, so let's check f of negative 3. So we got 2 times negative 3 cubed plus 11 times negative 3 squared minus 7 times negative 3 minus 6. Disaster. I got a 60. That does not equal to 0. All right, now let's check f of 6. All right, so we got 2 times 6 to the third plus 11 times 6 squared minus 7 times 6 minus 6. Let's compute that. No, 780. That does not equal to 0. All right, let's go. F of negative 6. We got 2 times negative 6 cubed plus 11 times negative 6 and then minus 7 times negative 6 and then minus 6. All right, let's compute that. Oh my gosh, we got a 0. We have a winner, winner, winner. Yes. Okay, so that's good sign. All right, so therefore, we know that x minus negative 6 is going to be a factor of f of x, which is same thing as x plus 6 is a factor of f of x. I'm doing this so that we can get the rest of the zeros, but for now we know for sure that negative 6 is going to be a 0 of our f of x. So let me write that out. So 1 at the 0 is x equals to -6. All right, so let me just box that before I don't lose it. Okay, so now since x plus 6 is a factor of f of x, that means that x plus 6 should divide f of x very nicely. All right, now in order for me to find the remaining zeros, I need to divide f by x plus 6. So here I think we can use the synthetic division, so let's do it. I am going to use synthetic division on this. So I'm going to have a -6. And then let's write down the coefficient of our f of x. So we have a 2, 11, -7, and then -6. All right, so I'm going to draw the line. Let's do it. Drop down the 2. And multiply -6 and a 2, you're going to have -12. Add, then I'm going to have a -1. Now if I multiply -6 and a -1, I'm going to get 6. And then add, then I'm going to have a -1. And -1 times -6 gives us 6. And look at it, remainder is 0. So again, remember that our answer here must start from degree 1 degree less than our f of x. So this is going to be the coefficient on x squared, x, and then constant. All right, so let me just write that out. So this is going to be some x squared and then x, and then this is going to be the constant. All right, so what have we just found out? So therefore, we can rewrite our f of x as x plus 6 and then x squared minus 2x squared minus x and then minus 1. And I think we can factor this a little bit further. So you're going to have x plus 6. And then this one should be able to factor. So you're going to have a 2x and an x. So what do we need? -1 and +1. Does that make sense? You're going to have positive 2x squared and then plus x minus 2x and then minus 1. Yep, that makes sense. All right, look at it. Now we can find the other zeros now. So we can already say that our 0 of this is going to be -6 because we already have that. All right, now let's take care of this one. So our 0 of that, let me just work it step by step. You're going to set that equal to 0. And then you're also going to set x minus 1 equals to 0. And then you're going to solve for x. So here our 0 is going to look like it's -1/2. And then another one is 1. Oh, really? So maybe I should have checked at p over q to be +1 to begin with, because 1 is going to be a 0. My bad. That would have been done a long time ago. So I'm so sorry to torture you. But you know what? We got here. Okay, so let me just box that. Okay, so I think we're done. Now, you're probably asking is this, right? How do you know that there are no other zeros? Okay, so here is the thing. If the degree of the polynomial is 3, you will have 3, at most 3 real zeros. All right, now sometimes you can have 1 real zeros and then 2 complex zeros. But in this case, we're all going to have 3 real zeros, which are -6, -1/2, and a 1. All right, so therefore, I'm going to write the answer here. The zeros are x equals to -6, -1/2, and then 1. We did it. All right, and here we go. Now let's go to our agenda number 5, going over the linear factorization theorem. It says this: let f of x be a polynomial function. Then f of x will have the same number of factors as its degree, which is same thing as that your f of x will have the same numbers of zeros as its degree. Now, so far we have been talking about the real zeros of polynomial. Now what we're going to get into is, yes, we can have a complex zero. So that's what we're going to talk about by using the linear factorization theorem. Here is the complex conjugate theorem that we're going to be using. It says, if the polynomial function f has real coefficients and a complex zero in the form a plus bi, then the complex conjugate of the 0, a minus bi, is also a 0. So this theorem is telling you is this. Suppose you get one complex zeros. That means that for sure the conjugate of that 0 will also be a 0. So if you're going to get a complex zeros, then it comes in pairs. That's pretty much what the statement is telling you. Alright, I know you probably are so sick and tired of reading all the theorems and trying to understand it, but come on now, we're in pre-calc, we got this. Alright, so the next theorem state is this. Every complex polynomial functions f of degree n, which is greater or equal to 1, can be factored into linear factors, not necessarily distinct, of the form f of x equals a sub n times x minus r1 times x minus r2 x minus rn, where a sub n and then r1 to rn are complex numbers. So basically it means that every complex polynomial function of degree of n that's greater or equal to 1 has exactly n complex zeros, some of which may repeat. Now distinct means there is exactly only one. So if it says not necessarily distinct, that means that some of the factors can repeat. That's all it means. Okay, now what we're going to do is this. We're going to apply all these theorems to find the polynomial functions whose zeros are given. So let's do some examples. Example 4. Find a polynomial function f of degree 4 whose coefficients are real numbers that has zeros, 1 and another 1, and negative 4 plus I. Alright, so applying all the theorems that we just learned, since we're talking about the degree 4 polynomial, that means that yes, we will have 4 zeros, including complex numbers. So let me just write that out. So now we're given 3 zeros, so we're missing one of them. If you recalled one of the theorem that we just went over, the conjugate pair theorem, it says that if negative 4 plus I is a 0 of f, then its conjugate also must be a 0 of f. So in this case, by applying the theorem, we know that negative 4 minus I must be a 0 of f. Now, since they're all zeros of f, that means that f of 1 equals to 0, and f of negative 4 plus I equals to 0, and then f of negative 4 minus I must be a 0. So, by the factor theorem, if f of c equals to 0, then x minus c must be a factor of f of x. So with that said, we should be able to write our function that we're looking for as a times x minus 1, because 1 was the 0, and then that repeats, so let me just write it out as x minus 1 again, and then x minus negative 4 plus I, and then times it by x minus negative 4 minus I. Oh boy, we got some algebra to do. Let's take one thing at a time. Okay, so first what I'm going to do is let's just multiply this out first. All right, so let me just go over here. So we're going to have a times, now if I FOIL that, I'm going to have x squared and then minus 2x and then plus 1. All right, and then let me just write the rest of it. You got x minus negative 4 plus I, and then x minus negative 4 minus I. All right, next, let's just multiply these ugly ones together. Now let me just copy and paste what we got so far. We have a and then x squared minus 2x plus 1. All right, are we ready to do this? We're going to multiply that out. You know what? Before I do that, let me just simplify what's in the bracket first. I might have an easier way to compute this. So if I distribute the negative sign in, I'm going to have x and then plus 4 and then minus I. And then on the next one, if I distribute that negative, I'm going to have x plus 4 and then plus I. So far, so good. Now, x plus 4, both of them, they're being added, right? So it doesn't matter if I put a parentheses just around the x plus 4. You're like, why? You'll see why in a minute. This will be a lot easier for us to compute. So let me put a little parentheses around x plus 4. All right, so now let's take a look at this again. Now, if you remember the difference of two squares formula, remember it says that if a minus b, a plus b. Now, that's going to be a squared and then minus the b squared. Do you all remember that formula? If you don't believe it, you can just FOIL it out. All right, so think of it in this way. I am going to take this x plus 4 as our a. So pretend this is our a, and then our b is going to be our I. So this is going to be B, and then this is going to be B. So look, you don't have to FOIL it out and deal with the nastiness. All I have to do is to use that formula. So let me just try to rewrite this again. Let me just bring it over here. So you're going to have an A, and I'm just going to copy and paste this portion. All right, so now what I'm going to do is a squared minus b squared, where our a is x plus 4, and then our b is going to be I. All right, so that whole thing's going to equal to a squared, which is same thing as x plus 4 squared. Maybe I should put it like that. And then minus I squared. Now remember that I squared was -1, correct? Okay, so let's use that, and furthermore, let's multiply this out. All right, and then I'm going to replace the I squared with -1. All right, so we got this already. So this is going to be a times x squared minus 2x plus 1. All right, so be careful here. X plus 4 whole quantity squared means x plus 4, and then another x plus 4, and then you're going to have a minus I squared. So you're going to have a minus 1. So far, so good. All right, so then here you're going to have a times x squared minus 2x plus 1. All right, then here what we're going to get is, if I FOIL that out, I'm going to get x squared and then plus 8x and then plus 16, and then it's going to become plus 1. So let's keep going. So this is a times x squared minus 2x plus 1, multiplying here by x squared plus 8x and then plus 17. We're almost there. All right, I know this is going to be a big old polynomial, but now what we're going to do is we're going to multiply these out. All right, so let's do step by step. So this is same thing as a times, I don't know why I put the bracket there, but whatever. So you're going to have x to the 4th and then plus 8x cubed. Do you see what I'm doing? I'm taking x squared and then distributing to each term of the second polynomial, and then next I'm going to take -2x and I'm going to distribute to each term, and then lastly I'm going to take 1 and distribute the 1 over. All right, so that's what I'm doing. So here, what do we get? X to the 4th and then plus 8x cubed and then plus 17x squared. All right, now I'm going to multiply -2x to each term, so you're going to have -2x cubed and then minus 16x squared and minus 34x, and then distributing the 1, so you're going to have plus x squared plus 8x and then plus 17. All right, now all we have to do is combine the like terms. So let's do this. So let's go with x to the 4th. X to the 4th is all by itself. All right, now let's go with x cubed. We got an 8x cubed, and then what else we got? -2x cubed. Anything else? Oh no, so that will give us, what is that? Plus 6x cubed. All right, now let's go with x squared. We got a 17x squared minus 16x squared and then plus x squared. So that will be plus 2x squared. All right, and then what about the x's? Oh, sorry, that's 2x squared. Let me just right? All right, and then the x's, where are the x's? Okay, so we got negative 34x and then plus 8x. What the heck is that? Is that negative 26x? And then the constant term is just plus 17. Done. Look at that. Now your a can be anything, okay? Your a can be positive 1, negative 1, whatever you want to. So here we go. Here is the polynomial function of degree 4 whose coefficients are real numbers, and that has the zeros of 1 repeating, and then negative 4 plus I, and then negative 4 minus I. All right, the very last topic that we're going to talk about is Descartes' rule of signs. So let's see what it says. If we let f of x equals a sub n x to the n plus all the way up to plus a sub 0 be a polynomial function with real coefficients, then the number of positive real zeros is either equal to the number of sign changes of f of x or is less than the number of sign changes by an even integer. And the second statement says that the number of negative real zeros is either equal to the number of sign changes of f of negative x or is less than the number of sign changes by an even integer. So what Descartes' rule of signs doing is telling us the relationship between the number of sign changes in our given function f of x and the number of positive real zeros. Now, what is the sign change, right, of f of x? So let me just give you an example here. Suppose we have a function f of x equals x to the 6 plus x cubed plus x squared plus x minus 1. So let's talk about the sign change. All right, so from here, we're going to start out with the positive in between the first two variables, and then the next one is plus, so there is no sign change. All right, and then from this plus to the next, it's another plus, so there is no sign change, but the next one, it's going to go to plus to a minus. So there is one sign change in this whole entire f of x. So let me just write that. So this is the only sign change. Now let's read the Descartes' rule of signs. It says that the number of positive real zeros is either equal to the number of sign changes of f of x. All right, so here our number of sign change is 1. So it's possible that we can have just one positive real zeros, right? Or it says, or is less than the number of sign changes by an even integer. All right, so here's my number of sign change, right? Now, is less than a number of sign changes by even integers. So the even integers are 2, 4, 6, and so forth. Now, the closest one will be 2, right? The smallest one. So if I subtract 2 from 1, do you see that we're going to have a negative value? So is there such thing as a negative numbers of sign change? No, there is no such thing. So this tells us that there is exactly one positive real zeros in f of x. Now, what about the number of negative real zeros? Well, we're going to have to apply the rule number 2. So in order for us to do that, let's see. The number of negative real zeros is either equal to the number of sign changes of f of negative x or is less than the number of sign changes by an even integer. So if you want to count how many negative real zeros that we're going to have, instead of just writing down f of x, first what we need to do is we need to compute f of negative x. All right, so let's write that out. So this is going to be negative x to the 6 and then plus negative x cubed plus negative x squared plus the negative x and then minus 1. Now we need to simplify before we count the number of sign changes. So this is just going to be positive x to the 6 and negative x whole quantity cubed is going to become negative x cubed. And then negative x whole quantity squared becomes positive x squared. So you're going to have plus x squared. And the next one's going to be minus x and then minus the 1. All right, now it's simplified enough. So what we need to do is we need to compute the sign change. I apologize. Earlier, I think I might have started from this positive to the next, right? But really, sorry, I skipped this part. You have to count the sign on the very first leading term as well. So here, this is positive, right? So it didn't change anything. So that's why it went from starting from here earlier. But in general, you're going to have to start from the very beginning sign. Okay, so here's our plus, and then next sign is going to be minus. So here's one sign change. Now I have a negative, and it's going to go to a positive. There's your second sign change. All right, and then it's going to go to positive to negative. So that's your third sign change, and then negative to negative, it doesn't change. So there are 3 sign changes here. But let me just draw that out. So there's a plus here. So this is one of them, and then 2, and then 3 of them. All right, so here, number of sign changes is going to be 3. All right, now let's read the statement of the theorem. It says that the number of negative real zeros is either equal to the number of sign changes of f of negative x. So our the negative real zeros, we could have 3 negative real zeros. But let's read the next one. It says, or is less than the number of sign changes by an even integer. All right, so if the sign changes are 3, then if I subtract by an even integer, so that will be minus 2. So 3 minus 2 will give us 1. So the rule is telling you that we could have just 1 negative real zero as well by the second statement. Okay, so let me just write down the result. By the Descartes rule of signs, f of x could have either 3 or 3 minus 2, which would be 1 real negative zeros. Let's take a look at an example. Example 5. Use Descartes' rule of signs to determine the possible numbers of positive and negative real zeros for f of x equals negative 3x to the fourth minus 5x cubed plus x squared minus 2x minus 10. So let's see the possible numbers of positive zeros that we could get from our f of x. So for the positive zeros, right, you just check the number of sign changes of given function f of x. So let's do it. So right now, the sign on the front is negative to negative, no sign change. Negative to positive, there is 1 sign change. And then it's going to go from positive to negative, so there is another one. And negative to negative, so no sign changes there. So the number of sign changes here is going to be 2. So that implies that we can have either 2 positive real zeros or 2 minus 2, which will be 0 positive zeros. So here it is. F of x has either 2 positive real zeros or no positive real zeros. Now let's check for the negative zeros. Sorry, I meant negative real zeros, and then here it's positive real zeros. I just didn't write the real part. Okay, now how do I check is this. Instead of f of x, you need to first compute f of negative x. So let's just do that. Then you count the number of sign changes. So we have f of negative x is negative 3 times negative x to the fourth minus 5 times negative x cubed plus negative x squared minus 2 times the negative x and then minus 10. All I did was I just replaced our x with the negative x. That's all I did. Now we're going to simplify. So this is going to be negative 3. Now negative x to the fourth is going to become positive x to the fourth because you're raising negative to the eventh power, right? So this is going to be just negative 3x to the fourth. Now the next one, negative x whole quantity cubed, is going to become just negative x cubed. So here you're going to have plus 5x cubed, And the next one is going to be plus negative x whole quantity squared becomes just a positive x squared. So you're going to have plus x squared. And next one's going to be plus 2x and then minus 10. All right, so now we're going to count the number of sign changes. So let's starting from the very beginning. Here is 1. All right, and then it's going to go to plus, nope, and another plus to plus, right? Do you see what I'm talking about? Negative to positive, and then positive to positive, no sign change, positive to positive, no sign change, but the last one, yes, it's going to go to positive to negative. So number of sign changes is going to be 2. All right, so that implies that f of x has either 2 negative real zeros or no negative real zero. So this is what the Descartes rule of sign tells us. Now remember that if the degree of the polynomial is 4, that means that we should have 4 real and or complex zeros. So if we have 2 positive real zeros and 2 negative real zeros, all the zeros are going to be real numbers. However, it could go 2 positive real zeros and no negative real zero, right? So that means what then? Other 2 zeros has to be a complex numbers. So I'm going to be organizing and make a little chart. All right, here's my chart. The first column is for number of positive real zeros. Second one is for negative real zeros, complex zeros, and the total of zeros, no matter what, we better have 4. Okay, so keep that in mind. So I'm just going to write it as how many options would I get? Just 4 options, right? 4, 4, 4, and a 4. All right, so suppose that we have 2 real zeros because, 2 real positive real zeros. Okay, so then we can also have 2 negative real zeros, right? That means what? How many complex zeros are we going to have? None. So I'm going to put a 0 there. All right. Now, suppose we have 2 positive real zeros and no negative real zeros. That means how many complex zeros that are we going to have? 2. All right. Now, next, suppose that the positive real zeros, we don't have any. And that means, and then another choice for the negative real zeros was 2, right? So suppose that's 2. That means that our complex zeros, we should have 2 complex zeros. Does that make sense? All right. So I'm just taking, all the possible combinations that we can get so that the total zeros will add up to 4. All right, and the next one, suppose we have no positive real zeros and then no negative real zeros. So that means how many complex zeros are we going to have? We're going to have 4. So we got 4 options going on. Well, now the question is this. Well, what's our true answer? Are we going to have all 4 real zeros or 2 real zeros and then 2 complex zeros, right? So we don't know yet. So the best way to do it is by graphing it out. Remember, zeros are the x-intercept, right? But anyways, let me just graph this out and see what our true answer is going to be. Okay, so here is the graph of our function that we just talked about. All right, so let's take a look at this graph. Does it intersect the x-axis? Do we have any x-intercept? We don't have any, right? So that means that there are no real zeros at all. So which indicates that all zeros, all 4 zeros are all complex zeros now. So here's my final answer. No x-intercept implies that no real zeros. So therefore, that implies that all 4 zeros are the complex zeros. How did you like this problem? It's pretty crazy to think that someone could actually come up with this kind of a theory, But anyways, we went over so many different important theorems in this section. So I am going to stop here. And good job, everyone. And if you have any questions at all about any of the theorems or any of the topics that we talked about, please let me know.